Hi, thanks for coming to chat with us. Do you want to start off by just introducing yourself, telling us what you're working on, who you're here with, how's NeurIPS been?
Yeah, thank you very much for having me. My name is Matthew Tivnan. I'm a researcher and lecturer at Harvard Medical School and Massachusetts General Hospital in the Department of Radiology. My research focus is image reconstruction, specifically CT image reconstruction. So my background, I got my PhD in biomedical engineering from Johns Hopkins. So my background, I was working on hardware like X-ray sources and detectors and building imaging systems and doing reconstruction algorithms. So taking the raw measurement we get from CT scanners and reconstructing an image from it. But a lot of the math and the skills that go with that are like nonlinear optimization or, statistical mechanics or linear algebra. A lot of those are transferable to machine learning. So like over time, I've kind of increased the amount of research I've done on machine learning. And at this point, kind of my research specialty is generative models like diffusion models and flow models for image restoration and reconstruction in medical imaging.
Cool. Yeah, are you presenting something at this conference?
Yeah, we have a poster tomorrow. It's called System Embedded Diffusion Bridge Models. So if I can, I'll just go into describing that. So usually, if you're familiar with the basics of diffusion models, usually what you have is additive noise and optionally scaling the image signal down over time in the forward diffusion process. And then you train usually a score matching neural network to learn how to run the reverse time process, starting from noise, pure noise, and generating an image. So if you're doing unconditional generation, that means you just kind of sample a new image generated from the same distribution as the training. A lot of my research is in conditional image generation, so that means we have some outside measurements, like it can be anything. It could be like in CT, the images are actually like X-rays taken from many angles of a patient, and what we want to reconstruct is the three-dimensional distribution of the density or attenuation coefficient of that patient. But it could be anything. It could be like inpainting is a great example. So like if you just have a missing section of an image and you want to fill in what's there, well, it's conditioned on all the information in the background. So it's not just generating a new image, it's generating a new image that's conditional and consistent with some information. And usually the way that's done is by kind of thinking about the diffusion process the same way, where you have additive white noise in the forward process, and now the reverse process is conditioned on that extra information. That could be by providing it directly to the network, or it could be through various techniques to use an unconditional network and modify it during sampling. We have a different approach where we're doing what's called a diffusion bridge model. There's a few of these out there, or just bridge models in general, so you'll hear them called Schrodinger bridge model or just bridge models in general. And the difference here is that the forward process ends not on white noise, but something else. So you're going like distribution to distribution. And when you do the reverse process, you're just doing that same thing in reverse, whatever that is. So in our case, what we do is have a forward process that's designed to converge at the final time step to something that looks like an image that we would reconstruct with no deep learning. So mathematically, it's a pseudo-inverse reconstruction in a linear inverse problem. What's different about what we've done versus previous bridge models? We use a matrix formulation of the forward and reverse process. So if you read Yang Song's landmark paper, Score SDE, Appendix A has the general formulation, okay, and it's matrix valued diffusion rates, matrix valued drift rates. We use that general version, and what we do is we embed the system matrices that describe the imaging system which generated the measurements into the forward and reverse process. So yeah, that's kind of the general idea. And what that does, I will say, like, there's an important concept to understand this, which is that imaging systems have what's called a range space and a null space. So there are certain features of the image that we're trying to reconstruct that just don't exist in the raw measurements at all. Inpainting is an obvious example because like in that inpainted region that's like masked out, you just don't have any signal from the original image in that region.
There's no ground truth.
There's no ground truth, and the measurements that you start with just have no information to help you in that region. So that's what we call the null space. The range space is spanned by the measurements. It would be the background in an inpainting problem. And it could still have noise there. So you could still have noise in the background. Yeah, so what our model does is basically denoising in the range space and synthesis of a new signal in the null space. And so the way we do that is we craft the forward process to converge to, again, the pseudo-inverse reconstruction, or just the reconstruction we would get with no deep learning at all, kind of the starting point. It's usually going to be noisy, and it's going to have regions of missing data. And with this model, we can basically denoise and synthesize where needed.
Yeah, this is super. I have so many questions because I think, so I also recently had a healthcare project, generally interested in both methods and applications, and I feel like it's both harder and easier than you would think to take sort of an applied problem and come up with a novel machine learning solution that NeurIPS people broadly cares about.
For sure.
And I'm curious if you can talk a little bit about the process of going from, okay, you have this very concrete real world problem that you're trying to solve in the medical imaging space. How do we abstract out the machine learning question here and then turn that into something that, NeurIPS is going to understand?
Sure. Yeah, absolutely. I guess what I would say, one reason why I work in the medical imaging area is because it has a very positive impact and it has a very real concrete impact on patients' lives. So it is a healthcare medical application, and it becomes very important to produce high quality images. So let me give an example, in CT imaging, we expose patients to radiation. That comes at a cost to them. They were, exposed to some radiation. It's allowed for medical purposes, but we want to basically respect that and do the best we can with the photons that we get out of the scanner, basically. Do the best we can. So that, basically means image quality and fidelity to reconstructing the actual anatomy of the patient. It's not just a beauty contest. We're not just trying to make a beautiful, pretty picture, right? We're trying to make something that's going to lead to accurate diagnosis for concrete medical problems in medical images. So that's kind of what motivates me. When it comes to the research process, we have certain research projects going on where there are known concrete challenges, and kind of the approach that I like to take is to be driven by those problems and to think about how new techniques in this field can apply. And I like to try to apply things that are already out there, first of all, and then to kind of listen in the math for the empty spaces, right? Listen for where there's some missing piece of the puzzle. So for example, in this case, we did some research using an existing method called image-to-image Schrödinger bridge, and that one involves adding white noise in the forward process. And it just occurred to me from my background in this area that, in the range space, where you actually have measurements, you may not want to be adding extra noise in the diffusion process in those areas. So it kind of came naturally out of that. And how to make something that's of interest to people at NeurIPS, that's always going to be a challenging thing for sure. I guess if it solves a real practical problem that helps to enhance the perceived and real impact of your research when you submit something, so that can always help. And just staying up to date with whatever else is going on and make sure whatever you're submitting is actually, a novel and an interesting method that's useful.
Yeah. All right. Thanks for coming by and chatting with us. We have a little surprise for you.
Should I open it?
And while you're doing that, let's say everything in your research pipeline pans out. What does 3 to 5 years from now look like? Are we able to reconstruct everything? What's next after reconstruction? Yeah.
That's a great question. This is what I'll say, is that these new algorithms and deep learning models that we talk about at NeurIPS are actually going to enable new kinds of imaging systems. So things that we previously thought were impossible to do in the space of medical imaging, we're actually going to be able to do. That's my prediction, is like over the next 5 years, the fact that we have these relatively new tools like generative AI in image generation and conditional image generation, the fact that we have these new tools is actually going to feed back on the hardware. We're actually going to develop new kinds of imaging systems that are only compatible with that kind of reconstruction we couldn't have done previously. A golden ticket. Okay, awesome. Thanks so much. Thank you very much. Yeah, it was really fun. Thank you.